Hello. Hello. Yeah. Can you hear me? Hello. Okay. Uh, so we'll wait for a few more minutes and then we'll get started. We'll just wait for 2 more minutes. Yeah, thanks. Yeah. So hi everyone. I am Arpit and uh, I'll be your TA for this course, Introduction to Biostatistics. Uh, Today we are starting with our second live session. We'll be discussing some more practice questions relating to whatever has been covered so far in the course. If you have any doubts, feel free to stop me and ask whenever. So before we start, here are some important links. So the first one is the link to the live session that you're attending, and the second one is the link to the YouTube channel where the recordings of these live sessions will be uploaded. Uh, so I don't think I've uploaded the last one, but I'll upload both of them by tomorrow. And there's a Google Drive where all the study material for the live sessions are present. You can also find these links in the chat box and I think in the NPTEL website. So we'll get started. Unless anyone has any questions from last class or from any other topic that was covered in the class this week. If not, we'll just get started. So, yeah. So the first question is find the range of the following data. So we are given 9 numbers and we are asked to find its range. So what we have to do here is first we have to look at which one is the smallest. We have to find basically the minimum and the maximum. So here the minimum value is, I guess, 88 and uh, the maximum value that we have is 128. So the range is basically maximum of the data minus minimum of the data. So in this case, it will be 128 minus 88, which turns out to be 40. So the answer here will be option D, 40. Okay. So the second question is to determine the number of cells in a cell suspension. Random sampling was performed and the cells were counted. given below are the sample numbers obtained from the sample. Determine the standard deviation of the data and approximate it to the nearest integer. So we are given some data, which is basically some random experimental data, uh, where basically the number of cells are counted in the suspension. And what we have to do here is we have to get at the standard deviation of the data. So as we know that the standard deviation sigma for some data is given as xi minus x bar square, summation of that divided by n minus 1, since we are taking out samples and it's not from our population, right? And the whole root of that is basically the standard deviation. So if these kinds of questions come in the exam, it's easier to basically make a table and do these calculations. So for example, we can make a table by first adding, like putting the values of xi. So 15, 30, 40, 30. 28, 25, 34, 42. Okay, so here basically we are trying to find the standard deviation of this sample, and basically this is the formula for standard deviation. So these formulas you need to remember, and you need to be careful about. So there are two formulas for standard deviation. One is for the population, where basically the denominator here will be n. But here in this case, we are talking about samples that we obtained from the population, and therefore the denominator we'll be using here will be n minus 1. Right. So once we have xi, we can write a few things. First of all, n is basically 10. 10, yeah. Then we need to calculate, first of all, x bar. So that is given by the sum of all xi divided by n, right? So in this case, what we do is we basically take the sum of this. Say 29. So the sum here is 296, and n is basically the number of observations, which is 10. So our x bar or mean turns out to be 29.6. Right. So yeah. So next, what we need to do, since we are calculating the standard deviation, we'll also write the formula for that here. Standard deviation is xi minus x bar whole square divided by n minus 1, the square root of this term. So what we need to calculate next is xi minus x bar, and then xi minus x bar square. We'll basically square these numbers, what we get here. So x bar we know is 29.6. So what we do here is we subtract, so 15 minus 29.6, which will be minus 14.6, then 0.4 minus 1.6 minus 9.6. Right. So here we don't need to submit. We just need this as an intermediate. So when you're making these calculations in the exam, it might be easier to like do these instead of like trying to directly calculate and sum it up. It might be slower at first, but once you get used to it, it might be easier to do in this way. Right. So if you square this, what we get is 0.16 plus 0.16. 6. And then we have to sum this up. So, so so this turns out to be 1084.4. Right. So what we need to do now is just plug this formula in because now we have the summation of xi minus x bar whole square. So here, uh, 1 second. Yeah. So what we have here is 1084.4 divided by 10 minus 1 square root of this. We 0.4 divided by 9 square root of this. If we calculate this, so in the exam, you of course have a calculator with you. Mhm. And so we run 0.25 square root of this, which will approximately be, will be around 10.98. So it is, we have approximately 11. Let's see, 11 is as the option. Yes, 11 is there. So the answer here will be C, 11. Right. Um, and the next question is, a survey reported that the average commute time of employees in an office is 30 minutes. Given that the standard deviation is 5 minutes, determine the minimum percentage of employees that have a commute time between 15 and 45 minutes. Right. So in this question, what all do we know? We know that the average commute time of the employee, or which is the mean, is around 30 minutes. We know that the standard deviation sigma is around 5 minutes. Then we are asked to determine the minimum percentage of employees that have a commute time between 15 and 45 minutes. So in questions like this, where we are asked to like identify what is the percentage of employees or percentage of people within a given range, what we generally would need to do in this course is basically use Chebyshev's theorem. So it's slightly difficult to say, but basically what it says is that uh, if we are, mm, what is it? If we are looking at basically a distribution, any general distribution doesn't have to be normal, and we have the mean, and let's say we have a standard deviation around it. So what what the theorem basically says is that uh, so if for k is greater than 1, if we are taking intervals that are k sigma wide, so basically this will be mu minus k sigma, and this will be mu plus k sigma, right? So in this interval, so this will have some amount of data within it, right? So what this theorem says is that the amount of data, the number of points that are present here, is equal to 1 minus 1 by k square into 100%. So that much percentage of the data lies within these bounds. So k can be 2, 3, 4, and so on and so forth. It's not 1, it's greater than 1. So whenever we are asked questions like this, where we have to estimate like what proportion of the data or is present within a given range, we need to generally use this theorem. So in this case, what we need to do is we need to figure out, first of all, what is the value of k that we should be using. So the easiest way to do that is to basically use this formula, which is basically k is equal to limit minus mu by sigma. So limit is basically the upper or the lower limit that one of these we can take. So in this case, we'll take the upper limit. So we have a positive value. It doesn't matter. K will actually be the mod of this, any limit you take. So what we do is 45 minus mean, which is 30, divided by standard deviation, which is 5. So the value of k for this will be 15 by 5, which is 3. Right. So the value of k here will be 3. You can also see that, so 3 into 5 is 15. So 15 plus 30 gives us the upper limit, and 30 minus 15 gives us the lower limit, which is 15. So the percentage of data points that are present in this range, again, according to this theorem, is basically 1 minus 1 by k square into 100%. So in this case, k is equal to 3. So what we have is 1 minus 1 by 3 square into 100%. Right. Yeah. So, sorry, this turns out to be 1 minus 1 by 9 to 100%, which is basically 9 minus 1, 8 by 9 into 100%. This is approximately 88.89%. Right. So the answer here will be option C, 88.89%. Right. So anytime you have a question which looks like this, where you are basically given a mean and a standard deviation, and you're basically asked to find what is the proportion of data that is uh, present within a given range, you have to use this theorem mostly. Right. Yeah. Or if you're looking online, it's sometimes called Chebyshev inequality also in statistics. Like, and this formula works for almost all distributions. So irrespective of whether your data is normally distributed or however it is distributed, this formula works because this is the minimum estimate, right? So for example, if we use this formula to see what falls within two standard deviations, 2 sigma. So for basically k is equal to 2, we get 1 minus 1 by 2 square 100%. It's basically 1 minus 1 by 4 into 1%. It's 3 by 4 into 1%. It's 75%. Right. So what this means is within this two standard deviation, so mu minus 2 sigma, mu plus 2 sigma, 75% of the data should fall here. Right. But if you look at a normal distribution, within two standard deviations, we know that we get a much higher percentage than 75%. I think it's around 95. I'm not sure. Say 95, yeah. So within two standard deviations for a normal distribution, this number will be 95%. So what this theorem gives us is basically a lower bound or a minimum estimate of the number. And that's why again, like what we are asked here in this question is the minimum percentage. So if you are confused about these kinds of questions, you can also look at that to identify that, okay, maybe this is the place where we use theorem. So the next question is, the average number of focal adhesions in a cell were determined to be 30 in a study. If these measurements had a standard deviation of 10, what is the minimum percentage of cells that have focal adhesions between 10 and 50? So again, we see that we are asked, we are given the mean, we are given the standard deviation. We are asked what is the minimum percentage of cells. What is the basically minimum, like the percentage of data within a given range, which is here 10 and 50, right? So again, what we need to do here is basically use that formula. So first we need to estimate, we are given that mu is equal to 30, we are given that sigma is equal to 10. We need to estimate first k, which is given as L is explicitly right per limit minus mu by sigma. Actually, upper or lower, it doesn't matter, but yeah. So 50 minus 30 by 10, which is 20 by 10, which is 2. So K here is 2. So the percentage, minimum percentage of cells, percentage of cells between 10 and 50 will be equal to 1 minus 1 by K square into 100%. And K here is 2. So 1 minus 1 by 2 square into 100%. We just did this calculation some time ago. So the answer turns out to be 75. So this turns out to be 3 by 4. And the answer here is 75%. Just did it here. Great. Next question. A researcher is plotting obtained data with appropriate error bars. The standard deviation in her experiment was found to be 10, and the standard error of mean was found to be 2. What is the sample size used in her experiment? So we are given two things here. We are given the standard deviation, which is basically 10, and we are given the standard error of mean, which is basically 2. Right. So, okay, first let's understand what we mean by the standard deviation and the standard error of mean and how they're different. Then we'll come to the formula. So, okay, so basically, let's say we are talking about a population in a class, right? Simple example that we have a class of students where we are trying to estimate the height of the class, right? So since there are, let's say, 100 students in the class, we don't want to call everyone. We are just taking samples. So first, let's say we take a sample of 5 people and we get 5 random heights, for example, 100, 120, 131, 119, 118, something like this, right? So using these 5 observations that we first made by calling out 5 random people, let's say we called random roll numbers and we got this data. So from these values, we'll get a average height. Let's say it is mu1. So it will be the sum of this divided by 5, right? Now we put those students back in and we again randomly call another 5 roll numbers. And let's say this time we get values such as 133, 148, 110, 119, and 170. Right. So again, we'll get another mean for this set of people that we called now. And if you look at the numbers, you can be pretty sure that mean 2 will be higher than mean 1 because the numbers that we have here are in general higher than this value, the other numbers, the other set of numbers, right? So we know that these two means are different. But what we are trying to do is using these sample means, we are trying to get at the mean of the population. So X bar, for example, which might be the mean of the population. So that is what we are trying to get at. So which of these is a more reliable indicator of the mean of the population? Or how are these means distributed? That basically is the standard error. So for example, like drawing more on this, let's say we take 10 samples and we have 10 values for it. Let's say mu1, mu2, mu3, mu4 till mu10. So each of these individual samples we can basically plot on a number line, let's say. And we can have 5 different points. We can have the mean, which is in this case mu1, and we have a standard deviation around the mean, which is the sigma 1 for this set of data, right? So we'll have a mu1, we'll have a sigma 1. For this set of data, again, if we plot it on the line and we calculate these statistics, we might get another slightly different mean, mu2, and a slightly different standard deviation, sigma 2, right? Mu1, mu2, sigma 2, and so on and so forth till mu10, sigma 2. Now, what we do is, so this is for each of these random samples, right? Now, what we need to do is, if we basically take these means from these 10 random samples and we plot those means on another line. So what we have here is not the individual points, which are 100, 120, 131, not these points, but what we have here is mu1, mu2, mu3, mu4, and so on and so forth till mu10, right? Mu7 and so on and so forth. So the mean of the population ideally would be somewhere in this range, somewhere in the middle of this probably, right? And we have a deviation around this central value here for all the means of these populations of these samples that we collected, right? So this deviation here is basically called the standard error of means, right? Sorry. So that is how that is what we mean when we say standard error of means. So standard error of means basically tells us how spread our value of the mean that we get from this particular sample is, right? So the formula for standard error of mean, we can calculate, it might be slightly confusing, but we can calculate the standard error of mean for a given random sample for a single set of observations, for example, this set of observations, without having to make all these 10 different observations. And that is given by the formula, which is sigma divided by root over of n. So for this set of observations, whatever was the n here in this case is 5, sigma here is sigma 1. So sigma 1 by 5 by root over of 5 will give us the standard error of means from this set of data points, right? So that's all we need to understand about standard error of means. So coming back to the question, what we are given is basically we are given that the sigma or the standard deviation is 10 and the standard error of means is 2. We know that the formula is standard error of means is given as sigma by root over of n. So we can say that n is, if we take n to the side, bring standard error of means to the side, sigma by standard error of means, and we have to square both the sides. Because once we take n here, so the next step would be n is equal to sigma by sigma. From here, we can come here, which is n is equal to square of sigma by c. So we are asked what is the sample size. So we are asked to find n. So in this case, it will be sigma is 10, the c is 2, square of this, which is 5 square, which is 25. Answer given in option B, 25. Right. Next question. The average blood glucose level in a healthy male after fasting is 85 plus minus 15 milligram per deciliter. A patient suffering from type 1 diabetes was found to have blood glucose level of 120 milligram per deciliter. Right. So find the z-score and comment whether the observation is an outlier. So the z-score of any value. So what we are given here is basically 85 plus minus 15. So mu here is 85, which is our mean or average. And sigma here is 15, sorry, which is our standard deviation. So we are given the value is basically x, which is the value, which is 120. So find the z-score. So the z-score is given as x minus mu by sigma. This basically converts our observation using the mean and standard deviation of our distribution, sample distribution, to a range which can be compared to the normal distribution, right? So the z-score is basically comparable to the normal distribution. And when we have a z-score of greater than 3, is generally when we say that the data is an outlier, right? So what we need to do here to calculate the z-score is just put in these values. So 120 minus 85 divided by 50, which is 120 minus 85 is 5 divided by 15, which will approximately be 2.33, right, or 2.34. So in this case, the answer will be C, 2.34, and it is not an outlier because the value is less than 3. Right. In the exam, if you are, what is another way to like quickly remove options is to look if these pairs make sense. So for example, if you actually would have calculated and arrived at a value of 1.34, you won't say that it is an outlier, right? Because we know that z-score of greater than 3 is considered to be an outlier. So this option inherently can't be right or has very high chances of being incorrect. So you can inherently remove these options and look only in these options. But yeah, this is a simple calculation, so you can just do this. But in more complex questions, if you want to eliminate options, this is a good way to eliminate options. Okay. So the area under the curve for a normal distribution, A is always a positive value. B is ranged from -1 to 1. C is equal to 1. And D is equal to the arithmetic mean. Right. So we are talking about a normal distribution here, right? Here, yeah. So for a normal distribution, the what we have asked is the area under the curve. So since it is the area under the curve, it cannot be a negative value, right? And normal distribution comes in many shapes and forms. So the value is not exactly fixed. It is not equal to the arithmetic mean, which might vary according to where this distribution is placed. Right. So the answer here will be option A, which is the area is always a positive value. Right. The next is question number 8. Does anyone have any questions till now for any of these? Any doubts regarding the questions we discussed? Or any doubts regarding the class material also? Okay. So question number 8. 500 people were screened for oral cancer in a cancer awareness drive. Given below are ages in years of diagnosis of the individuals who tested positive for the screening. Calculate the values for the first quartile and the interquartile range. So here we are talking about quartiles. So first quartile basically Q1 is given as 0.25 into n plus 1 at observation. Q2 is our median. 0.5 into n plus 1 at observation. So basically what this means is 25% of the data is below this point, Q1. This means that 50% of the data is below this point and the other 50% is above it. And Q3 basically means that 75% of the data is below this point. Right. So what we need to do is first arrange this data in ascending order. Then we need to get at what is the N. So N is basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So N here is 11. And we need to arrange the data in ascending order. Okay. 28. Okay. Fifty-eight, 66. Right. So once we have sorted the data, arranged it in ascending order, we are asked to calculate Q1 and the interquartile range. So the interquartile range IQR is given as Q3 minus Q1. Right. So we need to calculate Q1 and IQR. So we need to calculate all three Q3, Q1, and IQR. So Q1 in this case will be 0.25 into n plus 1, which is 11 plus 1 with observation. So basically 0.25 into 12, which is 3. So the third observation, 1, 2, 3. This is our Q1. Q3 is basically 0.75 into 11 plus 1 observation. So 0.75 into 12, which is 9th observation. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 58 is our Q3. So the IQR will be Q3 minus Q1. This is 34. 34 is 24. So we are asked Q1, which is 34, and IQR, which is 24. So the answer here will be option A, 34, 24. And question is, which of the following formulae represents the second moment about the mean? So when we say a moment, basically MR is given as summation by R divided by N. So this is a moment of a data. When we talk about the second moment, we are talking about M2, which is summation square by N. And when we are talking about, so this is the second moment. Right. And when we are talking about second moment about mean, we are basically subtracting the mean here. So summation y minus I R square divided by A. So this is one of the formula which basically comes close to this. So this is a representation, whereas the other ones are not. So this is the third moment. And this is just something else. It's not a moment. Wait. Question 10. The second sample moment about the mean is also defined as A, kurtosis, B, skewness, C, variance, and D, standard deviation. Right. So the second moment about the mean is again basically what we saw before, which is basically, let's say we are using x now, x minus x bar whole square, sum of this, x2 dash. So divided by n. So this is basically the formula for the variance. So the second sample moment about the mean is called the variance. And the rest of the things are defined differently. So standard deviation is root over a variance. Skewness is given as M3 divided by M2 raised to the power by 2. And kurtosis is basically M4 divided by M2 raised to the power 2. Okay. So variance is basically M3 divided. So what should be M3 dash? Four divided by square. So these are basically dimensionless quantities or ratios that basically tell us different things about a distribution. For example, the skewness tells us if how the distribution is skewed, if it has a long tail at one end versus a short tail at the other one. Right. So this distribution is positively skewed because there are more points towards the end here. And the kurtosis basically tells us the skewness. The kurtosis talks about the peakedness of a distribution. So what it basically tells us is the distribution like this, or does it have a peak, or like what kind of peak it has? Is it higher or low? That basically tells us that is basically related to the kurtosis. So that's how we measure the peakedness of a graph. So question 11, what is the variance of the data set? 5, 8, 8, 9, 6, 10, and 5 approximate to the nearest integers. So again, to calculate the variance, the easy way, what you need to do is psi, which is psi. We need to calculate the x bar, which is summation of psi divided by n. And here it's 1, 2, 3, 4, 5, 6, 7. So we equal to 7%. E 50 divided by 7, which is 7. Right. Then we are asked what is the variance. So the variance is given as xi minus x bar whole square, sum of this divided by 3. So here, since we are not talking about samples, we are talking that this is the full data set. So we use the formula of n and not n minus 1. Great. So xi minus x bar. Sorry. Is a 5 minus 7.14. 7 minus 7.14, which is 6. Then we have 6 bar whole square. So yeah, we have to use a calculator here, or seven minus 6. 6. Minus 6. So I would suggest like get used to using the online calculator that you will be given during the exam. I think in the NPTEL website itself, they will have a link to it somewhere. But since this is a statistics course, you are supposed to like make calculations of these kinds in the exam. So like just be familiar with the calculator so that you can easily do this too. So it's 22.85 sigma square here. 74 divided by n, which is 7. This turns out approximately to 3.2. This turns out to 6.2. If we approximate it to integer, it will be around 3. So the answer here will be option A, which is 3. Right. The next question is, if the standard deviation of a data set is 4, what is the variance? So this is a straightforward question. The standard deviation is basically root over our variance. So we are given the standard deviation, which is sigma, which is root over of variance. So variance is basically square of standard deviation, which is 16 in this case. The answer here will be option C, which is 16. According to the Chebyshev's theorem, what is the minimum percentage of data within 2 standard deviations in between? So we have done this before. We have look at this. So there are not a lot of different variations you'll get on these questions. It will mostly be 2, 3, 4, or 5. So in the case here, we have considered k is equal to 2, and it turned out to be 75%. So again, it is 1 minus 1 by k square whole into 100%. That is the percentage of data within two k standard deviations from the mean. So mu minus k sigma 2. So this percentage of data occurs in mu minus k sigma to mu plus k sigma. And if we input the value of k is equal to 2, we get 75%. So the answer here will be option B, 75. Question number 14. Which of the following would cause the standard error of mean to decrease? Increasing sample mean, increasing sample size, increasing standard deviation, decreasing sample size. So again, if we look at the formula for standard error of mean, the formula is given as standard deviation divided by root over of n. So here we have two terms. One is the standard deviation of the data, and the other thing is the number of samples. Right. So the sample mean cannot affect it. Sample size and the standard deviation can affect it. So option 1 is not the correct option. Then let's see what happens when we increase the sample size. So if we increase, n goes up and the value of SCM decreases because the denominator here is increasing. So this is correct because sorry, we want to see when the standard error mean decreases. That is when this increases, this decreases. We'll check the other options also in case if multiply correct as well. So increasing standard deviation, increasing the standard deviation would increase the standard error mean. So this is not the correct answer. Again, decreasing will have the opposite effect. So this is not the correct answer. The answer will be option B, increasing the sample size. Right. Number 15, a data set has a mean of 50 and a standard deviation of 5. What is the z-score of a value of 65? So we are given x is the value which is 65. Sorry. We are given mean is equal to 50 and we are given standard deviation is equal to 5. So the z-score will be x minus mu by sigma, which is 65 minus 50 by 5, which is 15 by 5, which is 3. So the answer here will be option C, 3. Next question is, the standard error is a measure of A, spread in population data, B, spread of sample means around the population mean, C, maximum value in data, and D, most frequent data point. So the maximum value in the data is the maximum value. It is not the standard error. The most frequent is the mode. The spread in population data is the population standard deviation, right? So the standard error is basically this. And we also know that because of the example I told, where basically when we are doing an experiment, we are picking out people randomly. So we are taking random samples. Then we take mean of those samples. And the distribution of this mean is what gives rise to the standard error of means. Right? So what we are talking about when we are talking about standard error is basically we are talking about a spread of means of different random samples that we took around population means. Right. Number 17, which of the following statements is true for a normal distribution? A, mean equal to median equal to mode. B, area under the curve is less than 1. C, it is always skewed. D, it is a bimodal distribution. So it is not a bimodal, it's a unimodal distribution. Area can be equal to 1 or greater than 1. It's just not negative. And it is not skewed at all. It is perfectly symmetrical. It's photo, but yeah. So the correct answer is option A, mean, median, and mode are the same for a normal distribution. Question 18. A data point has a z-score of -2. What does this imply? So a z-score of -2 means that so option A, the value is 2 standard deviations above the mean. B, the value is 2 standard deviations below the mean. C, the value is equal to the mean. D, the value is an outlier. So the answer here will be option B. The value is 2 standard deviations below the mean. So that is what a z-score basically means. So if you have a distribution like this, and you have a mean basically, and let's say you have a z-score of 2, -2, which would fall somewhere here. So that means this is 2 standard deviations below the mean. This is the mean, right? In a box plot, if the median is closer to the bottom of the box and the upper whisker is much longer than the lower whisker, what does this suggest about the data? So before we answer this question, we'll talk about box plots. So this is rotated horizontally. So if you have to make it vertical, you have to rotate it this way so that the minimum is down and the maximum is up. So imagine, right? So essentially, when you're plotting a box plot, what you plot is a box like this, which is bounded by the lower quartile, which is Q1, and the upper quartile, which is Q3. What we have here in the middle is a line, which is the median, or also the Q2, right? So what this means is that 50% of the data is below this line and 50% of the data is above this line. Here, 25% of the data is here. The rest of it is here. Again, 25% of the data is here. The rest of it is there. Right. Now this whisker indicates what is the minimum value. So if the minimum value, sometimes it can fall within this range, so you don't have a whisker. Sometimes it can fall here, so you have a whisker. And generally, the length of the whisker is basically 1.5 times the quartile value, right? Mm. Sorry, it's 1.5 times the interquartile range. So Q3 plus 1.5 times IQR will basically give you this number, which is the maximum the whisker can go up to. And this here will be Q1 minus 1.5 times IQR. And we know that the IQR is nothing but Q3 minus Q1. Right. So if there are data points which are lower than this value, then we represent them as X or points below. And if the data points that are greater than this value, again, we represent them as X or points above. And these are basically our outliers. This is an outlier. So there's basically a box plot. So what we are asked is, in a box plot, if the median is closer to the bottom of the box. So let's draw a box. Again, when we draw a box, this is the Q1, this is the Q3. The median is closer to the bottom of the box. So Q2 or the median is here. And the upper whisker is much longer than the lower whisker. So the upper whisker is, let's say, till here, and the lower whisker is shorter, let's say, till here. What does this suggest about the data? A, the data is symmetric. B, the data is negatively skewed. C, it is positively skewed, or there are no outliers. So since we have not talked explicitly about outliers. We cannot discredit this. The data might have outliers. We are not talking about it. So the data is not symmetric for sure because the median is not towards the center, right? If the data is symmetric, the median would come towards the center of the distribution, right? So this thing you can imagine it as a distribution itself. Actually, it will be helpful if I plot it horizontally. Okay. I just have to do it again. So we have Q1 here, Q3 here, median which is closer to this. Then we have a small whisker here, and we have a large whisker here, right? So now imagine we are imagine how the distribution would look like, right? So a quartile basically tells us how much data is below that point. So basically 25% of the data is below the Q1. So 25% of the data is here. The other 25, which is again till the 50% of the data, is somewhat around here, which is the median. And then you have a, sorry, the next 25% of the data is spread out in this region till Q3. And the last 25% goes beyond. So what we have is basically a distribution like this, which is basically a positively skewed distribution because it has a tail towards the right. Now, if we had a, so this looks like a well-balanced box plot. If we were to imagine what the distribution that generates this box plot looks like, we would say that basically, let's say the median is here. 25% of the data is still here. The other 25 is looks like this. Again, here we have the same. So this is more or less a symmetrical distribution, right? So if there is positive skew, what happens is the tail here gets longer. So these things start to come here. So because the tail is longer, the values that you encounter here are more spaced apart. So this goes back and the median clusters or goes towards Q1. So what this basically means is I draw these lines. So ideally, this is not the right curve, but 25% of the data is here, 25% is here, 25% is here, and 25% is here. But the length here is much more, so the data is more spread out, and the length here is much less, so the data is less spread out. It's more aggregated. Right? Okay. So this is a straightforward question. The z-score formula is dash. As we have talked about it before, the answer is yeah, A, x minus mu by sigma is the formula for z-score. Right. So does anyone have any questions or doubts till now? So this week you had taught about R also. So a little bit of introduction to R you are giving. In the exam, you won't be allowed to use R. But you should know how to use R because it will help you with your projects and analysis. Right. So I'll just basically walk you through a few things. So can you guys see the screen? I opened a browser. So basically, this is the website where you can go to download R. This is r-project.org. Here, basically, you can uh, see the latest version is 4.5.1. And here, basically, to download, you have to basically click here and choose any of these websites. For India, I think they have these two websites which you can use. And once you click that, it should have three options: R for Linux, Mac OS, or Windows. Right. Depending on your system, you can download and install this. Then what you should install is basically RStudio. So this is from this website called Posit. So basically, again, they mentioned that you have to first install that and then install RStudio. So you can directly just go to this website, click here, download and install R. It will take you back to this place. And then you can basically click this and the download will start. And you will basically install RStudio. And this is basically how RStudio looks like. Um, Can you guys see the screen? Okay, once we talk about this RStudio, we'll go back to the questions, right? Um, for whoever has missed what, we can just cover that again. So here in RStudio, you have different places. I have rearranged mine in a certain way, but uh, what you will generally find is that uh, you have a tab like this, which will store all the variables or the things that you are basically creating and using currently in R. This is basically the console. This is where you type in commands in R. And then we have this other window where you can basically write script. So a script is basically a file that you can write and run. So for example, if I say x is equal to c of 5 and x. So instead of going and typing all that here and trying to do that repeatedly, for example, if I have to run this set multiple times, or let's say I was writing a piece of code or a piece of analysis, which I have to reuse again, or basically run again and again. So I can just write it here in this window and basically press run. So it will run it one by one in the console. And we see that here what we have done is we have created this value X, which basically stores this list, which is 1, 2, 3, 4, 5, which you can see here, which reflects in the environment tab here. And if I run the second line, it will basically print X to the console, which is 1, 2, 3, 4, 5. Right. So you should go through the uh, lecture material. Actually, just a second. So the slides for the lecture material are available online in the website, NPTEL website. So there you can go and download the slides for this week's lecture, and basically you will get these slides. Right, if you do that. So there you can find all these different commands that were taught in the class, and we'll also go over it once here. So the first thing is we are taught how to create vectors. So So if you put a pound sign or a hash in front of a line in this script, it is basically considered as a comment. So it is not executed as code. It's basically a comment that you are Sorry. Yeah. So this is how we can create a sequence. Then there are other ways to create a sequence. For example, P is equal to 6, um, equal to 1, equal to 7, y equal to 1. So what this will do is basically create a sequence from 1 to 7 and by increasing 1 in each step. So if we run this, we print B, we see that it is 1, 2, 3, 4, 5, 6, 7. Now if we change this by to 2, it will increase in steps of 2. So if we run this again, what we have here is 1, 3, 5, 7. So it's increasing in steps of 2. Right. Then you can also use something called repeat, which is REP 1, and you have to give a value to how many times you want this thing to be repeated. So times is equal to 10, and if I run this, we'll get a list of 10 ones, right? And you can basically combine these operations. It's actually, there's another thing. So you basically do 1 is to 3. This is also another way of writing a sequence. So this, if I do 1 is to 5, this is basically the same as writing this, right? I run this, you see that there's a sequence 1 to 5, and it is repeated 5 times. So we get a longer sequence like this. Sorry. And then we can basically combine these operations. So let's say we want to repeat a sequence which is alternating. So what we'll do is basically we'll write sequence here from equal to 1 to equal to 7 by equal to 2. So what we are doing now is we are going to repeat this sequence of numbers, which is 1, 3, 5, 7, 1, 3, 5, 7, 3 times, right? If I run these, we get basically 1, 3, 5, 7, 1, 2, 3, 7, 1, 3, 5, 7, right? Then we have simple operations. So we have, let's say we define a list, which is 5. So we run it. This is basically a 1, 2, 3, 4, 5. So if we do our addition, a plus 1 will basically give us 2, 3, 4, 5, 6. So it basically adds on to each of these entries. Similarly, if we do a minus 2, it will again basically give us minus 1, 0, 1, 2, 3. It subtracts 2 from each of them. If we do a multiplication, which is a into 3, it will give us values which are so all the elements are multiplied by 3 here. Then what is it? Now let's say we have A and we have X that we have created earlier, right? Now we want to add these two. So basically, if I do A plus X, what we get is element wise, everything is getting added. So 1 is getting added to 1, 2 is getting added to 2, 3 is getting added to 3, 4 is getting added to 4, 5 is getting added to 5, right? So it's not adding across different columns, but it's basically adding each of these columns together. Similarly, if I do A into X, I'll have all of them multiplied. So 1 into 1, 2 into 2, 3 into 3, 4 into 4, so on and so forth. Right. Again, so if I do exponentiation, which is basically raising A to the power, that's not easy. It's basically e to the power 8. Right. So e to the power 1, e to the power 2, 3, 4, 5, and so on. Right. So it does, again, element wise, it does the addition. Right. Now, if you want to read a file, what you can do in RStudio is basically here you can go and press import dataset from Excel. and it can basically you can browse where to go and open any file. You don't have any files now to open. The other thing that you can basically do is basically uh, write this code. So read.csv, file.choose, and if I run this, basically it opens up a window from where we can choose the file to open. Right. Then the other very useful thing that we can do using R is basically calculate simple statistics. So for example, let's say we have X is equal to so let's say we have a set of data. We run this, we basically get this set of data. So what we can do is if we take mean of X, we basically give you the minimum value, which in our case is 0. If you type the max of X, it will give you the maximum value, which is 9. You type mean, it will calculate the mean, which is 3.5. If you do ST, it will give you the standard deviation, which in this case is 2.4. So instead of making all those calculations, what we could basically do is just put these values in R and calculate these things. So for example, what we have here is 5, 7, 8, 9, 6, 10, and 5. Let's say I'm putting all these values here. 6. Great. We calculated the variance to be 3. Now we are taking this and we basically say variance and we press put y. So y, variance of y is 3. So right. So here it is using the n-1 formula. That's why it's arriving at 3.8. What we used was n, which is why we got 3, because we are looking at it like a data set. Right. Then what else do we have? So if you want to plot a data, you use this function called plot. So say plot x and y. So actually you can't plot something that has different length. So x and y, I will have the x which is will run this again. We are redefining a and x, so you can see that it is updated here. A and x have changed. Now we say plot this, we get this plot here. So this window is where you get all the plots. This is also where you can go browse files. You can install more packages. So R has these packages, which are basically pieces of code that you can use in your work, which other people have written and shared. Then we have this help place where you can basically go and search for anything. So let's say I wanted to know about how the variance function works. I'll just go search for var, and it will tell me that variance takes x, y, nar, m, and q's. So x is a numeric vector. So here in this case, we are giving a numeric vector. Y is no default or a vector which is compatible with x. Then should missing values be removed or not? Then use is basically what to use. And method is like there are different methods of calculating the variance. What kind of method do you want to use and so on and so forth. Right. So here you can go, you can type mean, you can type other functions and you can see how they are used, what are the arguments they take, what is the value that they give, and what are like other functions which are similar to it. Now, again, if we are plotting, we have options to do things such as we can insert the title here. X lab is basically X is label. I lab Y X is label. Right. And we can plot this. You see, now we have a title here. We have a label to x-axis. We have a label to y-axis. Right. And basically, if I write x lim is equal to 0 to 2, or let's say 0 to 4, notice what happens to the graph. I run this. No, you have to write this C because you're giving it a list of numbers. It's like slim takes a list of numbers. So if I remove this now, what we have is a plot like this, but if I add that, I'll make it to 3 to make it more dramatic. Now you see that the limits of the x-axis have changed. It was earlier from 1 to 5, now it's from 0 to 3. Right. You can basically use these limits to change how you plot things and so on and so forth. Right. Then there are other things that you can look up in R, such as bar plot, box plot, and so I wanted to just plot the box plot of y and just do this, and we get a box plot. Right. So this is basically telling us that for y, which is our data here, the median is around 7. Then we have a larger tail here, a smaller one here. And that means there are like values here which are have much higher, but there are not a lot of values here which are smaller than the Q1. Right. And then we can also do bar plot of y that will basically give us bars. So for each of these values, 5, 7, 8, 9. So 5, 7, 8, 9, 6, it gives us bars, right? And if we do a hist of y, what we will get is a histogram. So now what we have is frequency. So the frequency of the number 5 is 3. Actually, this is 5 to 6, so it's 3. So 1, 2, 3. The next one has 7, which is this. 8, which is this. 9, which is this. And 10, which is this. Right. I've had to add a few numbers here. And I run it again. When you plot the box plot, you see that it has changed because now we have added more values around 1, 2, 3. The bar plot looks different of the new values we added. And the histogram has changed. Now we have values from 0 to 10. And this is how they're distributed. Right. So that's it about R for now. We'll go to question number 1. Does anyone have any doubts or issues installing R? Okay. So someone asked question number 1. So this is question number 1. What we have here is find the range of the following data. So we are given some data. So for the range, what we need to do is find the minimum value and the maximum value, and we take the difference between the maximum and the minimum. So the maximum here is 128 and the minimum here is 88. So maximum minus minimum is 128 minus 88, which is 40. So the range here is 40. Is that clear? So does anyone have any other questions or doubts? 2 and 3, sorry. So question number 2 is to determine the number of uh, cells in a cell suspension, random sampling was performed. Given below are the number of cells obtained, determine the standard deviation. So here we know that the formula for standard deviation is xi minus x bar whole square divided by n minus 1, the square root of this whole thing. Since we are talking about a sample, we are using this formula where n is the denominator is n minus 1. What we have done here is just mention these values xi, so 15, 30, 43, and so on. And basically, here we sum it up, we get 296. N is equal to 10 because we have 10 different numbers here. X bar is summation of xi by n, which is 296 by 10, which is 29.6. Then to calculate the standard deviation, we need to calculate xi minus x bar whole square, and that's sum of that. Right. So what we do here is we do xi minus x bar. So 15 minus 29.6, 30 minus 29.6, and so on. We list all the values. Then we square each of them. and then sum it up. So the value we get here is 104.4. So that divided by n minus 1, which is 10 minus 1. So root over of that. So we get 10.98, which is around 11. Is that clear? Like, was that okay? In question number 3, a survey has reported that the average commute time of employees in an office is 30 minutes, given that the standard deviation is 5 minutes. So we are given the average commute time, which is the mean, which is 30, and we are given the standard deviation, which is 5. We are asked to determine what is the percentage of employees which have a time between 15 and 45, right? So what we need to do here is basically uh, use Chebyshev's theorem. So what that tells us is that for any distribution within k standard deviations, the percentage of points that you will have, the percentage of data that we'll have is 1 minus 1 by k square into 100%. So this is the percentage of data within this limits, within these bounds. So mu minus k sigma to mu plus k sigma. So we are given mu here, we are given sigma here. We have to find what is k. So k in this case will be the limit minus mu by sigma. Limit can be the upper limit or the lower limit. So here we take 45, 45 minus mu by sigma, and we get the value of 3. So the value for k here is 3, and we put that into the equation, the Chebyshev's theorem. So what we get is 1 minus 1 by 3 square into 100%, which turns out to be 88.89%. Right. Was that okay? Okay. So when we are talking about populations, so for example, in this case, we are told that what is the variance of the data set, right? So in this case, let's say like we are assuming that the full data set is given to us, which is this numbers, right? So in this case, when we are calculating the variance, we'll treat this as the population, as the full data set. And therefore the formula that you'll use will have n not n minus 1. But if you look at the first question here, what we are asked is random sampling was performed and cells were counted. Given below is the number of cells obtained from a sample, right? So this is data from one sample. In that case, we use n minus 1. So in statistics, what you have is basically generally you have a population. For example, as the standard example, we have a class of 100 students whose heights we want to know, right? So this is basically our population. And since we cannot measure these 100 people, what we'll do is we'll basically take samples out of the population. So samples are X number of students for which we'll measure the height, right? So we'll get X values. I'm sorry, N number of students for which we'll measure the heights. And N is very less than 100. Not very less, N is less than 100, right? So we are taking a subsample, a sample out of this. So in this case, to calculate the variance, you use N minus 1. But if you have data for all 100 people, right? So you have data from the population. In that case, the standard deviation you'll calculate as N. That the denominator will be N. And in this case, it will be N minus 1. So this is basically done because when you take a sample, so the value that you are getting might be higher or lower. So to adjust for that factor, because we are trying to estimate the population values from this, we take standard deviation as divided by n minus 1, which gives us a more conservative approach. Right, conservative limit. Okay. So to install R, you just go to this website. You can put it up in the chat. So you can just go to this website. Here you will basically, you need to download RStudio Desktop if you are planning to use it on your computer. So first you go here, step one, which is download and install R. You click here. It will take you to another web page where you can, based on your operating system, you can download. For example, I would choose this because I'm working on Windows. Then basically what you do is after you have downloaded, so once you click this, it will basically click here, basically download the package that you can install. It will automatically come up. Then you basically go here and you click here, which will again start another download. Sorry, which is the RStudio. So once you have installed R, then you need to install RStudio. And after that, once you open RStudio, it should look somewhat like this if you are on the latest version of it. Right. The one shown in the video might not be the latest version. The one shown in first class might not be the latest one. And actually, this also might not be the latest one, but this is one of the more recent ones. Right. Okay. Is there any other questions? Okay. If no one has any questions, uh, we'll stop here today and we'll pick up in uh, next time, next week. So no one has any more questions or doubts, right? Okay. So thanks for attending the class and we'll meet again next week, same time, and we'll discuss questions regarding the next week's classes. Thank you and hope I'll see you guys again. Bye.